Hello everybody. Today we are going to start particle motion. Particle motion is fairly straightforward, but don't be deceived. This unit does get substantially more difficult. So you may know from physics that position is usually your original function, and your velocity is the derivative of position, and acceleration is the derivative of velocity, and a jerk is the derivative of acceleration. So the first thing we're asked to do in this problem is to find the velocity at time t and at t equals 1 second. I think I accidentally pushed pause. So you're looking for the velocity at time t and then at a specific value of t. So we go ahead and we find v of t, which is just the derivative of our position. Now, believe it or not, I went to a grading where it became very clear that stating this relationship explicitly in the way I have on this page is crucial. You cannot assume that the person grading your paper, I keep accidentally pushing pause, I don't even know how that's happening. You cannot assume that the grader grading your paper knows that you know that the derivative of position equals the velocity. Don't make any assumptions about how smart you are relative to the grader or how smart the grader is relative to you. Well, I guess that's the same difference, but you know what I mean. Okay, so we found the velocity in general, and now we're going to find the velocity specifically when t is 1. And when we do that, we find that v of 1 is -4. But we have units mentioned, in our original question, so we need to talk about this in meters per second, or we need to put the units down. I guess we're not talking. When is the particle at rest? The particle is at rest when your velocity is 0. When is it moving to the right? When your velocity is positive. You will need to justify your answers. This means that you must use words. I know that those of us in math tend not to like words very much, so this is hard for us. Not all of us, just most of us. The first thing we're going to do is we are going to solve for t when our velocity is 0. When we do that, we see that we have something we need to factor. So we factor it however you know how to factor. Some of you can do it in your heads and some of you cannot. Factor however you prefer, whether you use box method, I think there's something called the American cheeseburger method. I teach using a little crisscross. It doesn't matter. Nobody's going to judge you for how you factor at this level. They are not looking at that unless it's one of your peers who's a jerk who thinks that you should be able to magically do it in your head, and you can just go ahead and punch them. Or maybe not literally punch them, figuratively punch them, however that may be. Because that's not very nice to make fun of somebody for how they factor, right? Right. Now we get to the tricky bit. We know that our velocity is 0 at 1/3 and at 2. So we look at a number line And we need to examine the signs of our function. And for the record, I'm doing this all in my head. So when t is less than 1/3, pick an easy number. I'm going to pick 0. So when t is 0, I get a negative in that first parentheses. I did not calculate the value. It is not necessary. I actually did, but it's not necessary. In this second bit of parentheses, you will also get a negative. A negative times a negative is a positive. And right there, my brain chose not to do the math. You don't need a value. That piece right there is positive. Now we're going to look at those same values between 1/3 and 2, or that same expression that I highlighted, underline highlighted, between 1/3 and 2. So I'm going to pick an easy number. I'm going to pick 1. When I replace t with 1 in the first expression, I get a positive number. When I replace t with 1 in the second expression, I get a negative number. A positive times a negative is in fact a negative. So our velocity is negative from 1/3 to 2. Then I come out to 2 and I pick a number. I'm going to pick 10. The first factor is going to be positive. The second factor is going to be positive. So your velocity is positive to the right of 2, or when t is greater than 2. It is really important right now to note on paper the words I'm about to say. Your sign does not always alternate. Again, your sign does not always alternate. Back in ancient times, also known as the 90s, this would be sufficient justification. Apparently, different professors and different teachers use this sign chart in different ways, making it impossible to grade properly. So, these days, you need to write down all of these words. Okay, the particle is at rest when t equals 1/3, 2 seconds. I think you really need the word or there, because it can't be 1/3 and 2 at the same time, because the velocity of t is 0 when t equals 1/3 or t equals 2. Now, I want to talk about notation real quickly. If you look, I use this because this is actually old-fashioned shorthand from, I don't know, the 60s or 70s. Don't use any abbreviations that are not standard abbreviations. If you use any abbreviations that leave any kind of doubt in anybody's mind about what you might mean, they will not be accepted. So make sure you only use standard abbreviations. They don't need to be shorthand, but they need to be standard. Like you see them commonly in textbooks, that sort of thing. Okay, the particle is moving to the right when t is an element of the set 0 to 1/3, 0 included, union 2 to infinity. You can either write it using the top notation, that's on top of it, or that's terrible, or the bottom notation. You do not need both. I would tend towards the bottom notation, and then I would continue by saying because v of t is positive on these intervals. Now you're asked to find the acceleration at time t and at t equals 1, and your acceleration, wrong color. Your acceleration is the derivative of the velocity, which is the second derivative of the position. It is important to write down that relationship. And your acceleration will be 12t minus 14. Specifically, we're asked to find the acceleration at time 1, and that would be negative 2 meters per square seconds. Now we're going to find the displacement of the particle between t equals 0 and t equals 1.7 seconds. There is a big difference between displacement and distance. For those of you who have not taken physics, if I, for example, walk to HEB and then walk home, my displacement is 0. If I walk to HEB and then walk home, my displacement is 0, but my distance is about a mile. Okay, we're first going to find the displacement, and the displacement of the particle between t equals 0 and t equals 1.7 seconds. It is important to notice on the previous page that the particle changed directions at 1/3. So we need to find, for displacement, we don't need to concern ourselves with that, but when we get down to distance, we need to remember that. I tend to notice it right away because that's a critical piece of information. So all we're going to look at with displacement is what we would typically think of as distance, and we're simply going to take our distance at 1.7 seconds and subtract our distance at 0 seconds. And we will see that our displacement, we moved to the left 3.604 meters. Then we need to explain it in words. So here we see that the particle had a net movement of 3 and 604 thousandths meters to the left from t equals 0 to t equals 1.7 seconds. 1 and 7/10 seconds. Ooh, y'all, I haven't taught elementary school in so long. Actually, I never have. Okay, find the distance traveled, which is all movement. So that's the example where if I walk to HEB and back, I have walked a mile. Even though displacement-wise, because I started and ended at the same point, there's no displacement in the HEB example. So we need to account for our movement to the left and our movement to the right. So again, we start at 0 until we get to 1/3, where we're moving to the right. This whole thing, we're moving to the right. Then from 1/3 to 1.7, and I know this is a janky looking number line. You can handle it, I promise. It kind of tweaks me out too. We are going to look at our distance from s of 0 to s of 1/3, and then our distance from s of 1/3 to s of 1.7. And s of 1/3 is 5, s of 0 is 5, s of 1/3 is 5 and 630 thousandths, and s of 1 and 7/10 is 1 and 396 thousandths. Now, in order to find that actual displacement, we need to look at the absolute value, because we're not taking into account whether it's moving to the left or the right. And when it's moving to the left, it's negative. But we need everything to be positive because we need to add up all of our distance regardless of whether or not they are positive left or right, positive or negative. So here we go. In this first one, we have 630 thousandths, and in the second one, we have 234 thousandths. And our total distance is about 4 864 thousandths of a meter. Note, please, that some of those numbers up there were approximations, so you need to put approximately in the answer. So now we see that the particle traveled approximately 4 864 thousandths of a meter from 0 to 1.7 seconds. All of those words are important. Okay. The particle moves along a horizontal line so that its position at any time t is greater than or equal to 0 is given by s of t equals 2t cubed minus 7t squared plus 4t plus 5, where s is measured in meters and t in seconds. When is the particle speeding up? The particle will be speeding up when v of t, or the velocity, and a of t, or the acceleration, have the same sign. Always. So we're going to look for where that happens. From the previous page, we know that our velocity is positive when t is less than 1/3 and when t is greater than 2. Now we're going to look at our acceleration, and our acceleration equals 0 when t equals 7/6. And that number is, right around there. I don't know, that's probably not a good approximation. Right around here? Sure. And we know that our acceleration, when we put 0 into our acceleration, we get a negative. So this whole bit down here is negative. And when we put in 2 for t, we are going to get a positive. So it's all positive over here. So when do they have the same signs? Well, let's split things up a bit so we can see it a little bit more clearly. And it's negative here, negative here. This is acceleration is negative, negative, positive, positive. Where do they match? They match right here when t is bigger than 2 and when t is between 1/3 and 7/6. It doesn't matter that some people get really tripped up in that negative sign. That's not what you're looking at. You're only looking at when are they the same sign. So they are the same sign between 1/3 and 7/6. Between 1/3 and 7/6, they are speeding up to the left. When I don't know why I'm saying they. When t is between 1/3 and 7/6, the particle is speeding up to the left. When t is bigger than 2, your particle is speeding up to the right. If I were teaching this in real life, I would be running all over the classroom demonstrating this. So I'm going to try to find a video describing this because it's really useful to see the demonstration of something speeding up to the left and speeding up to the right. Okay, the words are the particle is speeding up on 1/3 to 7/6, union 2 to infinity. Since V of t and A of t have the same signs on those intervals, these need to be complete sentences. However, instead of writing this 1/3, 7/6, union 2 to infinity, which I think is kind of foreign to y'all. I feel like your textbooks haven't used that very much. You could just say 1/3 t 7/6, comma. Ooh, I don't want to do that. 2 less than t. You could say that also. Those two things mean the same thing. Okay. Onwards and upwards. Okay. When is this particle moving to the right? This particle is moving to the right when your velocity is positive. And your velocity is positive when your factors multiply to a positive, so they need to have the same signs. And because you can't factor, you need to use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And if you have not had a teacher who has taught you how to simplify a square root without a calculator, shame on you, you're lying. Both Roblo and Greiger expect you to simplify square roots without a calculator. Now, I know we love to not imagine our numbers, but it is really important that you do not waste time getting too caught up in this. Try really hard not to get caught up in this. This first number is bigger than 0 because this, let me try to show you what I'm thinking about. The square root of 25, that's what 5 is, minus the square root of 19 is going to be some positive number. So don't try really, really hard not to put this in your calculator. Try to just imagine. That number right there has to be bigger than 0. So you've got 0 over here somewhere. It's bigger than 0, but it's not very much bigger than 0. Then over here, you have the square root of 25 plus the square root of 19. And the square root of 19 is bigger than 4, but it's smaller than 5. Because the square root of 16 is 4, and the square root of 25 is 5. So it's somewhere between 4 and 5. So we've got 5 plus, let's say 4.5 over 3. That is a number that is bigger than 2. So we know that that's bigger than 2. That's all we really need to know. Now we're going to look at our numbers. Our function, our velocity function. And we're going to look at what's happening there. And we know that if we were to replace t with that first one, we would have 0. Same with the second one. Our velocity is 0 right there. So let's just put in some pretend number. Let's put in 0 for t, and we are going to get positive 2, so that's positive. I don't usually do the number. I don't usually actually do the math, but in this case it was so easy. Now we're going to replace t with 2. We've got 12 minus 20 plus 2. Well, that's going to be a negative. It doesn't matter if you don't know the number. You need to use a lot of imagination because you don't want to waste time on those calculations. The actual numbers are not important. Now we're going to put in some crazy big number like 5,000. If we replace t with 5,000, that's going to be a positive number. When is the particle moving to the right? The particle is moving to the right when, here's a tricky bit for you. 0 is less than or equal to t is less than 5 minus the square root of 19 over 3. It is also, I'm having trouble remembering my words. It is also moving to the right when t is bigger. That's not right. When t is bigger than our other root. The little tricky bit there was that your time could actually be 0. Let's look back at the last page and compare. Uh-oh. I don't know. Oh, yikes. I'm writing all over it, aren't I? Velocity, last page before. Did we ever need to know that? Velocity. Oh, we did have less than or equal to. Okay. I don't even know if you followed what I was saying. That's less than or equal to because your time can actually be 0. But your time can't be less than 0. You don't have negative time. Now we're going to look at the distance traveled by the particle from t equals 0 to t equals 3. By the way, let me interrupt this program to let you know this is a former free response question. This is exactly the kind of free response question that you will have on the AP exam. Also, you can Google particle motion free response question calculus and a bunch of practice problems will come up. We know that our particle changes directions at 5 minus the square root of 19 over 3. We know that the distance between 0 and that first turning point where it changes directions, that distance is 209 thousandths. The distance between negative 2.791 and negative 15, that distance is 12.209. The total distance traveled will be 12.418, or 12 and 418 thousandths. I'm starting to practice that now that I realize I forget how to say numbers for real. Okay, so now we know with just that little bit of math, it looks a little bit like Algebra 1, that the particle, because all we did was really do a few calculations, the particle traveled about 12 and 418 thousandths units from t equals 0 to t equals 3. Because it wants you to justify the particle moved 209 thousandths units. It doesn't specify units. Units are usually, the label units is usually pretty important, right? Then 12 and 209 thousandths units to the left. Okie dokie. Now for a little Easter egg. Okay, I used to live in this tiny town. I encourage you to Google it. The entire town of 2,000 people. Not kidding. I don't know how I did it. I lived there for 6 years, and I taught there for 6 years. The entire school for the entire district is in one building, or it was in one building. And it is all decorated like a Swiss village. A lot of my students still speak Swiss German, they still speak Swiss German, Swiss German. which is a little bit different from German. And most of them would go home to Switzerland to visit their parents. It was a fascinating place to live. And I would encourage you to Google it, because holy cow, is it ever. First of all, it's super famous, which is weird in and of itself. And second of all, it is fascinating. Y'all take care. Bye.